Hi everyone, we are back again this week to talk about bivariate analysis, another way of describing our data set. So far we've been talking about univariate analysis, when we talk about measures of central tendency, when we talk about measures of variation. What we're doing is we're looking at one variable or construct at a time, and we're compiling data to share information about that one variable. How is that one variable reflected and talked about in our data set? When we move into bivariate calculations, as the title again, as the name of that term might again tip you off to, we're talking about two variables or constructs. Something I want to make mention of really quick that we're not going to go into in this introductory statistics class, but if you continue your statistical studies, you will encounter multivariate analysis, which is when we're including more than two variables. So I wanted to include that context just so you know that there's a lot of different ways of describing data. Again, in this introductory statistics class, we're focusing on univariate and bivariate as some of the most common ways that we use descriptive statistics to describe characteristics of our data set. Again, if you continue in this route, if you ever decide to pursue a PhD, for example, you'll learn a lot more about how to include more than just two variables as well. So univariate analysis, some of these we've looked at in examples already. The average hourly wage of high school seniors would be one variable that we're looking at, average hourly wage. How many dogs licked me in the park when I went to the dog park? We're looking at one variable there. A couple variables that we're going to talk about today as well are students' previous experiences with math and students' feelings about taking a statistics class. So again, those are variables of interest that we might want to describe with averages, with standard deviation, etc. Ways of describing student responses to those types of questions in our data set. When we move over to bivariate analysis, this is where statistics gets a whole lot more interesting. So this is where we get a look at how are two things interconnected? How does one thing influence the other? So is there a connection between previous experiences with math and students' feelings about taking a statistics class, for example? I would hypothesize yes, right? If I am somebody who's had terrible experiences with math historically in elementary school and middle school and high school, I'm going to have a lot of mixed feelings about entering a course at the college level where I'm going to have to focus on math in a way with statistics. So when we move into talking about bivariate calculations, we don't always need to talk about dependent versus independent variables. In some situations we do. So we're going to use this example a little bit in some of the content for today. And this is something that will come back up later on throughout the semester as well. So dependent versus independent variables come up when we talk about bivariate analysis because we're talking about how to compare two different variables. And sometimes we want to know which variable is doing the influencing and which variable is being influenced by the other variable. So when we talk about the terms of dependent variables versus independent variables, that's what we're referencing. We're referencing that one of those variables is the one that is dependent upon the other variable. So we're going to talk about this a little bit. We'll have an opportunity later on to apply this. But the key thing to know here, again, the words that we use in statistics come into play. Dependent variable is the one that depends upon the independent variable. So if you think about like what the word independent means, it means like they stand alone. Something is reliant on itself only. So the independent variable is the one that is doing the influencing. The dependent variable is the one that is being influenced. Okay, let's take a few examples of this to make sure that we're understanding these two terms before we continue moving on into talking about bivariate analysis. So the value of the dependent variable depends upon the independent variable. So let's take a look at a couple examples. And I will pause after I read the examples. I'd like you to think about, do you know what the answer is? What do you think is the dependent variable? Which do you think is the independent variable? And why? So here are the examples we're going to look at. The first one, a child's shoe size compared to their age. If we're interested in taking a look at these two variables and how they interact, which one is dependent and which one is independent? So which do you think it is? So shoe size depends on child's age, right? Like a 6-year-old child is going to have a vastly different shoe size than a 2-year-old child. So the shoe size is going to be dependent upon the independent variable of the child's age. Next one, how sleepy you are today compared to how well you slept last night. Which is the independent variable in there and which is the dependent variable in there? Your sleepiness level today is going to be dependent upon how well you slept last night. I mean, some other factors in there as well, right? But in general, how well you slept last night is going to be the independent variable. That's not the one that's being influenced. That's the one that's doing the influencing. Next one, number of credit hours you've taken compared to your expected date of graduation. Which is the independent, which is the dependent. Your graduation date is the dependent variable, right? So your graduation date depends on the number of credit hours you've taken. Finally, the hours spent studying compared to your grade. Your grade's going to depend on the hours spent studying, right? So your grade will depend on the hours spent studying. Okay, so these were pretty straightforward examples. Sometimes when we get into actual research statistical examples, it gets a little bit foggier to try and decide which is the independent versus which is the dependent. What I would encourage you to do is jot down whatever notes make sense to you to keep those terms in your head. Again, with statistics, I would encourage you to focus less on memorization, focus more on understanding. So just include these notes somewhere that you can reference back to later. And if you're in a situation where you're having to decide what's the dependent versus independent variable and you're feeling a little fuzzy and mixed up, I'd encourage you to just like take a step back, try and look at this example, look at the situation from a broader lens before trying to put those labels on the terms. Just think naturally. Okay, child's shoe size compared to their age, which is going to influence which? And that can help you start to figure out which is going to be the dependent versus which is going to be the independent variable. So take a step back, try to look at it from a real world context rather than holding those statistical terms in your head. And hopefully this is something that will make sense to you just from looking at the variables that are involved. So when we talk about comparing those two variables, again, sometimes it's really straightforward as to which is the independent versus which is the dependent variable. So here we're looking at a chart. We're looking at a trend chart over time between 2008 and 2009, not exactly the most recent data, but a chart that was straightforward that I could find. And this is looking at the sunlight in Nebraska compared to the average amount of coffee that the amount of coffee that the average American consumes. So kind of back to my coffee reference. And we can see, they don't totally, so the blue line is sunlight in Nebraska, the orange line is average amount of coffee consumed. We can see they don't totally align, like the lines are a little bit separate from one another. There are certain points in time where amount of coffee consumed increased, whereas the sunlight decreased. Other times where sunlight was really high, coffee consumption was kind of high as well. So we're not seeing an incredibly close relationship between sunlight in Nebraska and amount of coffee consumed. But if you had to identify an independent and a dependent variable here, what would you choose? So this is another way to think about this. Sunlight in Nebraska, the sun doesn't care how much coffee we drink, right? Like the sun has no conscious knowledge of how much coffee is being consumed in the United States. That's certainly not dictating how the sun is operating. So the sun is going to be the independent variable in this situation just by nature of the fact that it's the sun. And the average amount of coffee is going to be the dependent variable dependent upon the amount of sunlight. But again, if we look at this analysis here, we don't really see an incredible amount of relationship between the two. So this would be an example where we have an independent and a dependent variable, but it doesn't necessarily mean that the dependent variable actually is influenced by the independent variable. We'd want to do a little bit more exploring of this relationship to see, are these things actually related, or did we just throw a couple random images on a chart and say that there's a relationship here? So in other situations, it might not be so clear. We might not be able to answer what's the dependent and what's the independent variable. So if we're looking at precipitation rates, for example, here's another chart over time showing between 1979 and 2011, precipitation in Nebraska compared to precipitation in Iowa. So the pinkish line you see here is Nebraska. The yellowish line you see here is Iowa. Makes sense. These are very strongly related, right? We can see that the lines, not always perfect, but we can see that the lines tend to flow with one another. We can see that these variables are a lot more connected than perhaps sunlight in Nebraska and the average amount of coffee consumed by the average American. And actually thinking about that previous example too, the amount of coffee that the average American consumed, that's like beyond Nebraska. So it makes sense that people in California aren't being influenced by the amount of sunlight in Nebraska, right? So if we look at the bottom chart, we see an example of two variables that are a lot more strongly related together. Their connection, if we're looking at this from a bivariate lens, we can see that these variables tend to move together. When precipitation in Nebraska increases, precipitation in Iowa was also sort of high, and vice versa. This time period in 88 to 89, for example, not much precipitation in either. If we look at 1993, we had high precipitation in both. So we see that these two variables are pretty connected, but how would we decide which is the independent and which is the dependent variable here? We'd have to know like which direction the storm systems are coming in, and like, did the storms originate in Iowa or Nebraska? Does that even make sense? So there are going to be some situations where there's not a clear dependent and independent variable. Certain types of calculations, so at the univariate level, we don't have to think about this at all. When we move into bivariate analysis, there are certain types of calculations that it really matters that we know what is the dependent and what is the independent variable, such as regression, which we're going to very briefly touch on in this week's content. There are other times when it really doesn't matter, and we can look at the relationship between two variables without having to know which one was the independent and which one was the dependent. So we will move into some of those examples. But before we go much further, I want to throw a few more charts at you as we're moving into talking about bivariate relationships. So did you know that the divorce rate in Maine heavily correlated, heavily connected with the per capita consumption of margarine? So here again, we have a lovely flow chart. We can see margarine consumption very closely aligns with the divorce rate in Maine. How about letters in the winning words of Scripps National Spelling Bee correlated with the number of people killed by venomous spiders? Really interesting relationships, right? Again, very closely correlated. We see over time, number of deaths and average letters in this spelling bee winning word, very closely aligned. Also, per capita consumption of mozzarella cheese and civil engineering doctorates awarded. Wow, slow and steady all the way up. Okay, so all this leads to a very important point. Perhaps you already are having this in your mind as I'm talking about these relationships. Just because something is correlated, meaning that just because there's a relationship between two things, just because we can throw up a fancy chart and show that these two variables are very closely interconnected, they have a very similar relationship with one another, does not mean that causation is involved. So it does not mean that one of those variables is directly influencing the other variable. So this is where bivariate analysis gets a little bit more complicated, maybe slightly more confusing as well. We can observe the relationship between two variables, but we absolutely cannot say for sure with statistics that one variable causes the other variable to happen. This is why the underlying theory of statistics is so important. We have to think about the relationship from a real world lens. We have to have an understanding of the variables that we're looking at in order to make any kind of suggestion that one variable actually is influencing another variable. And this is an area where statistics really doesn't do a good job right now. If we think back to the content from the John Oliver video or some of the stuff that I covered last week, we can see that very often statistics is presented in a way that implies that one thing is directly causing another. So this will be true throughout our time talking about statistics, especially when we're talking about bivariate analysis. We're going to want to be really careful about how we're interpreting information. Even when it's presented to us as though one thing is directly causing the other, we still have to look at it from this broader lens of understanding about the world, about these concepts. There's a lot of different factors that go into establishing causation. There's some scientific processes that can help with that. But again, the most important thing is that we are using statistics as a tool to understand reality. We're not using statistics as a tool to define reality. Statistics, just like anything else, were created by humans, flawed, imperfect, and all of those things. We can use them to establish that two variables are connected and do have some sort of relationship. We cannot, without very rigorous methodology, determine that one thing is causing the other. So all of statistics is a bit like a hypothesis, actually, which we will be talking about much further on, or much more in depth towards the latter half of the semester in particular. So if you're curious where I got those random correlations, here's the website for that. You can look and see a whole lot more a lot of them are about death, so I'll warn you about that up front. They can be a little bit, I don't know, not exactly hopeful to look through, but they're called spurious correlations, which spurious means just happenstance, by chance, super random. So they're relationships, they're correlations that are clearly based purely on chance. And so they're a good example. They actually are publishing a book about these now. They're a good example in the statistical world about a way that people are creating conversation about the way that we're using statistics. And we need to be careful, again, that we're not implying causation when really correlation is at hand. Because here's the reality of the situation, right? Like, here's why that real world understanding comes into play, because there are often factors that are driving both. So when we looked at the chart of precipitation in Nebraska and precipitation in Iowa, of course those two things align because those two states happen to be right next to one another. It doesn't make sense to say that one caused the other or one led to the other, because they're two states that are geographically nearby. We would expect the weather to be similar. Same thing here. If we're looking at shark attacks and ice cream sales, it looks like they're very interconnected. Both can be explained by something else. When the sun is out, we want more ice cream. We also want to go swimming more often. The more often we're swimming in the ocean, the more often shark attacks are going to happen. So, very important point as we begin to talk about a couple of the main ways that bivariate analysis is conducted. So there's two calculations we're going to talk about today. We're going to continue to move in the direction of talking more and more about bivariate analysis, especially towards the latter half of the semester. But for now, for today's purposes, we're going to focus on a couple bivariate analyses that are most commonly used, correlation coefficients being probably the most common way that information is initially shared about the relationship between two variables. So correlation, again, is a fancy statistical term for relationship. You can actually interchange those words pretty easily. They basically mean the same thing. When we're talking about correlation coefficient, this is a specific type of calculation. So just like calculating the mean, the median, the mode, standard deviation, range, all of those are independent individual calculations that are used to describe one variable. Correlation coefficients are a specific calculation that are used to describe the relationship between two variables. And correlation coefficients tell us a couple things. They tell us how strong the relationship between two variables is, and we'll come back to it. They also give us some information about how those variables move together. Are they like precipitation in Iowa and Nebraska, where when there's more precipitation in Nebraska, also more precipitation in Iowa? Is that how these variables move together as well, or is it something different? So another thing to know about correlation coefficients, there are a lot of different specific calculations that people use to calculate this coefficient. Coefficient is basically another word for like a data point. We are going to focus on the most common type of correlation coefficient that is calculated, which is the Pearson correlation coefficient, named after a guy named Pearson. Again, there's other ways that people calculate a correlation coefficient. Statistics is very complicated depending on the type of variables that are involved. You have to be really careful about the types of analysis that are being used. Pearson is the most popular one. Just like when we looked at symbols for univariate analysis, the symbol representing the Pearson correlation coefficient is a little r. So we're going to end up with when a correlation coefficient is calculated, we're going to end up with a little r that is giving us the actual coefficient, that's giving us the actual data point describing the relationship between these two variables. So another super important thing to know about correlation coefficients, and here we're going to pull back to levels of measurement from our first week together. Correlation coefficients can only be calculated with interval or ratio level variables. So correlation coefficients can only be calculated with interval or ratio level variables. If we have a nominal level variable like like eye color or hair color or profession or hobby, if we have a nominal level variable, we can't calculate correlation coefficients. If we have an ordinal level variable, like education level, we can't calculate correlation coefficients. For this particular calculation, because of the way the numbers are calculated, we have to use an interval or ratio level variable. These are also sometimes referred to as continuous variables. If you remember back to when we talked about levels of measurement, interval ratio level variables were reflected by that little ruler thing. So continuous variable is one that is continuous, right? Like a ruler starts at whatever, 0 and goes all the way up to however many numbers it covers. A continuous variable is like that. It's numbers, right? It's just pure numbers that range, they go in order. You can measure the difference between them. Those are the kind of variables that we need when we're talking about correlation coefficients. So correlation coefficients, super helpful, really super interesting, but can only be used with certain types of calculations. Otherwise, we get into trouble, which we'll talk a little bit about as well. It's easy to do this in Excel. I'm going to show you how it looks to run this calculation in Excel. You won't be expected to do that, but I'll give you a little snippet of how that looks in just a moment. So with correlation coefficients, there are a couple pieces of information that they provide to us. They tell us the strength of the relationship, which we'll talk about in a little bit. They also tell us what's called the direction of the relationship. So here's where a positive correlation and a negative correlation come into play. And this would be specifically referring to, after the calculation is conducted, whatever that R number turns out to be. If it's a negative number, it's a negative correlation. If it's not a negative number, it's a positive correlation. So also known as direct correlation, whereas negative correlations are indirect correlations. Just like I was talking about with the precipitation in Nebraska and Iowa, ironically it's raining right now as I'm recording this video outside. When precipitation in Nebraska increases, precipitation in Iowa also increases, like they move together, right? Not that one is causing the other, but they're moving together. When there's more precipitation, they're likely to be more precipitation in both. When there's less precipitation, likely to be less precipitation in both. This is a positive correlation. When they move together, when one increases, the other increases. When one decreases, the other also decreases. A negative correlation is the reverse of that. A negative correlation happens when one variable increases and the other decreases. So let's continue with the rain example. Right now it's raining, it's pretty lovely outside, and yet there's no sun. So sunlight and precipitation would be an example of a negative correlation. When precipitation increases, sunlight decreases. When sunlight increases, precipitation decreases. Doesn't mean that they can't coexist. Doesn't mean that sometimes it's sunny and raining. Actually, it was a couple days ago. It was sunny and raining. But overall, they tend to move in reverse. They tend to move in opposite. So that's a negative correlation. All right, so the correlation coefficient tells us which direction the relationship. Is it a negative relationship or is it a positive relationship? The number itself also gives information about the strength of the relationship. So correlation coefficient ranges only from -1 to +1. So we're going to get a calculation. Our calculation is going to fall somewhere within there. The plus or the minus tells us the direction of the relationship, as we talked about. The value tells us the strength of the relationship. And there's a really easy way to remember what level of strength we're talking about. In general, a higher value is going to indicate a stronger relationship. Let's come back to this absolute value thing. But here's a chart. This is the same chart that's reflected in your book. This is a chart that I would encourage you, like, jot this down in your notes or save this somewhere on your computer that you have easy access to. You'll be able to use this information. You definitely don't have to memorize this information. But in general, here's the sort of agreed upon range of what constitutes a weak or no relationship as opposed to a very strong relationship. So if we calculate a correlation coefficient and it ends up telling us R equals 0.95, we know we have a really strong relationship that we're looking at. If we calculate a correlation coefficient, or somebody else does, and they get a value of 0.01, well, that's not a relationship at all. So the number value tells us the strength of the relationship. The positive or negative sign tells us the direction of the relationship. So to go back to this slide, we want to use the absolute value when we're talking about the strength of the relationship. So when we're interpreting this information, the strength of the relationship, we want to use the absolute value, meaning we just ignore the negative sign. So if we end up with a calculation that says negative 0.85, that's a very strong relationship. It's a strong relationship. No, wait. 0.85 is a very strong relationship. So it's a very strong relationship. It's also a negative relationship. but it's still a very strong relationship because to interpret the strength of the correlation coefficient, we ignore that negative sign. So 0.8, our calculation of negative 0.85 is going to be stronger than a calculation of 0.60 because 0.60 is within that moderate range. All right, so two pieces of information that correlation coefficients tell us. So referencing back to this lovely little chart here, look at that! We have correlation coefficients calculated in these images for us. So this is very similar to when we're looking at a correlation coefficient, we're going to look at how the data points map out together over time. How are they compared together over time? And then we're going to look at what is the actual R value that is calculated. So here we can see that there's a positive relationship because there's no negative sign. So when the divorce rate increases, consumption of margarine increases, and vice versa. When one decreases, the other decreases. We see that here. The lines flow together. Right here in 2005, they both had a little dip. 2004, they kind of had a little bump. Not really, but it's close enough. Very strong relationship, very strong positive relationship. And again, an indicator of why correlation does not equal causation, right? Because just because these two things are correlated doesn't mean that actually makes sense. We have to think about this from a real-world context as well. In reality, it's a spurious correlation, right? It's just a random coincidence that these two things happen to align. Okay, so if we're looking at a near perfect relationship, a very, very strong relationship, like in this previous example, the dots are really, really, really close together all the way down. The flow of these two variables very much aligns. So when we're looking at a really perfectly nice relationship, this is what it would look like. A positive correlation indicates that if there's a low score on both ends. If there's a high score, there's a high score on both ends of the variable. So this is a very directly positive relationship. As one increases, the other increases. Here we are at -3 and -5 something, and then we flow up to -2 to -3. So the numbers are moving together, right? They're moving together. Over here, it's the reverse of that. Over here, it's a negative correlation because when one side has a really high number, the other side has a really low number. If we look over here, this side has a really high number, whereas it would be reflected on a really low number on the y-axis. So negative correlation is going to move in that sort of a lineup, whereas a positive correlation, as the numbers increase, they both increase. Most often, however, we don't see a perfect relationship that looks like that. Most often, there's a little bit of a mix of the dots. So here, like the dots are in perfect alignment. That's very rare. Most often, we see something like this, and we have to kind of just generally interpret it. Of course, the R value helps, but if we're looking at the information as to how it's plotted, how are these data points plotted, we have to look and see, is there any kind of indicator, is there any kind of trend in terms of how these variables are connected? So this middle point is a reflection of there's really no correlation at all. We can't really tell when one variable is low what's happening with the other variables because they're really intermixed. Over here, we can see that there's a slight negative relationship where the high variables over here are low on this end and the low variables on this end, or the high variables on this end are low over here. Okay, so let's take a look at how this looks in Excel. So again, you won't be asked to do this, but I wanted to show you just how it looks in Excel. Next week, we are going to dip our toes into practicing a few calculations with Excel. We're going to stick to more basic calculations than correlation. Just wanted to show you how it looks. So in Excel, if I type in equals Corel, which is the way to indicate we want Excel to do this calculation for us, so we don't have to do it by hand, which is good news for us. I'm going to highlight the two rows of data that I want to include: happiness score and number of candy bars eaten. This is data I made up in case you haven't figured that out. So we have 5 people. We have 5 people that I asked. I had them calculate some sort of happiness scale, and then I had them tell me how many candy bars they've eaten. If I calculate this out, I get a perfect positive correlation. So let's see what happens when I actually map this out. If I insert a little scatter plot, it reflects exactly what we've been talking about. So it looks like there is a perfectly positive relationship. That is very true. We have an R equals 1.00. That's a positive relationship. It's a perfectly strong relationship. These two things are exactly correlated, not by coincidence because I designed these numbers myself. However, let's see what happens if we flip a couple. So right now, we see that there's a positive relationship. The more candy bars someone has eaten, the higher their happiness score, or vice versa. The higher their happiness score, the more candy bars they've eaten. Here, it's a little bit trickier to establish an independent versus dependent variable, though certainly we could hypothesize. But let's see what happens when we mix it up a little bit. Let's say we look at the highest happiness score and the lowest happiness score, and we reverse the number of candy bars eaten for those. So I'm going to plug in a 0 for this happiness score and a 4 for this one. Ooh, we can see it totally changes the relationship, right? Now it's reflecting, there's still a relationship. Our R value is 0.60, which is going to be reflective of a moderate relationship. So 0.60, it's a negative relationship now. So switching those two numbers totally threw off the whole thing because we're only looking at 5 people, right? So it's really easy to skew the data in that sort of situation. And now our chart is a little bit more blurry. It does look like there tends to be like a downward trend. We can actually tell Excel to add a little trend line for us. So it does indeed look like there's a bit of a downward trend. But again, if we're looking at this from a real world lens, 5 people is not who we'd want to base this information on, especially since it's so heavily switched our results to get an opposite finding about those two happiness scores, or the number of candy bars that those two folks ate. So that's an example of how this looks in Excel. We're going to focus primarily on interpreting information when it comes to correlation coefficients. I'm not going to ask you to do the calculation yourself. What I am going to do is present to you some information and ask you to tell me about how you would interpret that particular correlation coefficient. So to get a little bit more comfortable with looking at these kind of plot diagrams, these scatter plots, and thinking about how is this relationship reflected, how are these two things related, let's take a look at some examples. So here we have exam score and number of missed classes. And we don't have a Pearson correlation coefficient calculated for these variables, but we can look at the scatter plots and think about, we can make some guesses as to what direction do we think this relationship is flowing. So do you think this is a positive relationship or a negative relationship? It's a negative relationship, right? So the higher the number of missed classes, the lower the exam score on this particular random set of variables that I found with Google. On the other hand, the lower the number of missed classes, the higher the exam score. So these two things are working in reverse. We have a negative relationship here. Next up, car age and price. So here, the bottom line we see reflected the years, the car's age, I guess, car's age in years. And then on the other side, we see the price of the car. What kind of relationship is this? Negative again, right? As age increases, price decreases. They move in reverse. They move in reverse. How about this one? This is, I assume, some sort of sports thing. We'll say basketball. What kind of relationship is this? It's a positive relationship, right? So here we see the lower the height, the lower the weight. The higher the height, the higher the weight. Makes sense. How about this one? We'd probably have a smaller Pearson's R calculation here, right? The things are definitely, there's a very clear trend line in some of these previous examples, very clear trend line. This one gets a little bit blurrier. It's a little bit harder to see what's going on. We have some high scores, even with a very low math final at the beginning. It still kind of seems like this might be a positive relationship. I would guess like a trend line would end up something like this, but it would definitely be not as strong of a relationship because it's a lot less clear. It's a lot more scattered about. All right, how about this? Okay, so this is actually reflecting real world data. For the past 3 years I've been teaching this class. I've used a survey, which y'all will be taking a slightly modified version of as we practice Excel stuff for next week. This is looking at math rating and stats class rating, essentially all 3 years of teaching this class for the past several semesters. In the spring, I would ask students to rate themselves on a scale of 1 to 10 about how do you feel about being in the statistics class. just like y'all were asked to do in your opening application assignment. I also in previous semesters asked students to do the same with math. So rating, how do you feel about math overall on a scale of 1 meaning hate it to 10 meaning love it? So this is reflecting those responses. This is 3 semesters of data all compiled into one. We have a very fancy scatter plot. What do you think is happening here? What kind of relationship are we looking at? Well, since I did these calculations myself in Excel, I added a trend line. You can see it's a positive relationship, right? Not very strongly correlated. In fact, I also did a correlation coefficient for this and found the relationship was 0.51, which is, I think that's in like the weak range. If we flip back through, I'm not going to go back because it's a long ways back, but I believe that's in like the weaker range. So it's not a very strong relationship between these two variables, I think in part because of just the way that I asked the question was confusing a couple semesters. But we can see that there's a positive relationship. So the more positively someone feels about math, also the more positively they feel about being in a statistics class. So in this situation, what do you think is the independent versus dependent variable? If you had to make a guess, which do you think would be the independent, which do you think would be the dependent? So again, math rating was on a scale of 1 to 10. How do you feel about math? Hate it, love it. Stats class rating was on a scale of 1 to 10. How do you feel about being in the stats class? Panicked, stoked. My hypothesis would be that math rating is going to influence stats class rating. So if I come into, again, if I have terrible experiences with math and I feel really badly about math and I don't want to do math ever, looking at numbers just kind of stresses me out, gives me some anxiety to begin with, I'm going to have some pretty mixed feelings about taking a statistics class. So I would hypothesize that the stats class rating is the dependent variable and the math rating is the independent variable. But again, this is one of those questions where we'd have to do some thinking. We'd have to think about the underlying theory of what we're looking at here before we can make some of those assertions. Another point with correlation coefficients is that sometimes strange correlations happen. So there's some variables that we're going to get really wonky scores with, not because there's no relationship between those two variables, but because maybe correlation coefficient isn't quite the right calculation to use. So if we're looking at something like performance and anxiety, for example, a low amount of anxiety sometimes is correlated with a low amount of performance. If I really don't care about something, I might not try very hard at all. If I don't have any anxiety about how I'm going to do in, I don't know, a homework assignment or a speech, I might not try very hard. So that would reflect this kind of low end over here. If I have a moderate amount of anxiety, that might be a motivating factor for me to perform better. However, it gets into that sticky situation where if my anxiety gets to be too high, then my performance is going to suffer because of my anxiety, right? So you have a curvilinear, what's called a curvilinear relationship happening here, where it's not very well reflected with this particular correlation because the relationship between these two variables is a little bit more complicated. Similar situation here. This is actual data that I don't know where it came from and when it was conducted. Again, Google is a lovely tool to find all kinds of these types of examples. Where we're looking at the relationship between average number of hours of sleep at night and performance on a reading test at the second grade level. And we can see that students who slept really poorly did not do so well, but also students who slept a lot did not do so well. So similar finding here. The relationship is not going to be very well reflected with correlation coefficients. We're going to end up with like a Pearson's R calculation of something like 0 because you can't tell. There is no linear relationship happening here, right? It's more complicated than that. There's a sweet spot essentially of amount of sleep you want to have or amount of anxiety you want to have, where at the other end of the spectrum, things start to deteriorate. So here is how our calculation would look for these types of different relationships. So another really important thing to know with correlation coefficients, it doesn't lend itself well to relationships that are complicated like that. It doesn't lend itself well to curvilinear relationships where the relationship dynamic changes depending on how much of something there is, how much sleep there is, or how much whatever else there is. Also, very often with correlation coefficients, we want to look at two variables, yes, but very often we want to look at more than that. So a very common way that correlation coefficients are reflected in the literature, this is the last thing we'll look at for now, is a correlation matrix. So your book talks about this. We're going to practice reading some of these and interpreting some of these because this is usually how information is communicated when it comes to correlation coefficients. Essentially, this is just a table reflecting all the possible calculations that could be made based on the type of data that they had available. So all this is, again, it has to be continuous data, so it has to be that interval or ratio level information. So when we're looking at income, education, attitude, vote, all of these are somehow reflecting a scale or some sort of assessment. So vote, for example, I mean, this example is from your textbook, so I don't think it gives this context, but vote and attitude, for example, could have been some sort of survey where they end up with like a likeliness of voting score on a particular range, or attitude about, doesn't even say what the attitude is about, but attitude about voting, who knows, on a particular range. So this is reflecting all of the different relationships between those four continuous or interval ratio level variables. So we have four variables that's reflected here in this correlation coefficient. One thing to know about these correlation matrices, one thing to know about these is if you look down the center line, you'll see perfect relationships all the way down. The reason for that is because if you look at which cell, like if you look at this particular cell and you look at which variables is it showing the relationship for, it's showing the relationship for income with income, right? So if we're looking at a correlation between the same variable, it's going to be perfect because they're the same variable. So when you see this one down the middle, you'll know to ignore that. It's just the variable repeating itself. And actually, if you look at these scores on the side, you'll see it's like the mirror image, essentially. So here is education correlated with income, 0.574. Same thing here. Income and education, 0.574. So you really only have to look at half of this correlation matrix to understand the relationship between the variables at hand. Sometimes the researchers will actually only give you half the chart anyways. They won't even show the repeat numbers just because you don't really need that, right? All right, so let's look at one example here. Education and income has a positive relationship, meaning that the two moved up together, but it's still a sort of weak relationship, right? Whereas if we look at something like income and voting, it's a very weak relationship, but it's a negative relationship. So a correlation matrix is used to present all of those different R calculations, all those different Pearson R calculations within one chart so that we can get a really quick and easy way of interpreting a lot of different data, a lot of different dynamics. All right, so here's one real world example that we will look at for now. This is from a study looking at police officers and their spouses and partners, specifically looking at secondary trauma within these populations. So it's looking at secondary trauma as a result of somebody being a spouse or a partner to a police officer. So essentially looking at, being a police officer is a stressful, traumatic experience. Of course, when we work in those kinds of stressful, traumatic jobs, we sometimes bring that home. We share our experiences with our spouses, with our partners. Very often, vicarious trauma can happen within those types of relationships. That's what this study is looking at. Feel free to pause and read the abstract information if you want a little bit more of understanding of what we are going to be looking at here. But this is a lovely little table looking at Pearson correlations among variables of interest. So a couple of things to know. SP secondary trauma is going to be referring to spouse and partner secondary trauma. So this is looking at the result, the impact on the spouse or the partner of being exposed to trauma secondarily, right? Like as a secondhand experience. The spouse or partner isn't the one experiencing those stressful, traumatic situations directly, but they do because someone that they love, their spouse or partner, is the direct person involved in those situations. So secondary trauma is referring to that. It's referring to the type of trauma you might get if you have a spouse or partner who's working in some really traumatic experiences. So it's looking at spouse or partner secondary trauma. So anytime you see SP, that's what it's showing. All right. I actually haven't read through this table yet either. So let's both take a pause for a moment. Again, this is the last slide we'll look at with correlation coefficients. Let's both take a pause for a moment, do a little looking at the numbers that are reflected in here and see what you think in terms of an interesting relationship. And I'll highlight a couple that are interesting to me as well. One more thing to note, sometimes they do this, sometimes researchers do this. Instead of the previous correlation example we had, you saw they just like repeated the words income, education, attitude, vote, income, education, attitude, vote. Sometimes researchers instead will number the items on the side, and then they won't repeat the words again up here. So when you see number 5, for example, it's referring to number 5 down here, the spouse or partner baseline level hostility. So baseline hostility would be, I don't know exactly how they measured hostility or what that's reflective of. We'd have to do some digging into the study to understand how they calculated that. But it's looking at the measure at baseline, so the measure at the start of this study. Okay, let's take a pause for a moment, see what you find. I mean, it's kind of hard to tell without understanding some of the information behind the study, right? Like we see a really high correlation over here. Total violence at 12 months might be reflective of violence within the relationship. See, I didn't include quite enough information to understand some of these details, so it's a little difficult to assess. But if we look at, for example, like baseline depression in spouses and partners, so this would be level of depression at the beginning of the study, 0.55 positive correlation with secondary trauma at 12 months. So what I interpret that as is the spouse or partner. If a spouse or partner was more depressed at the beginning of the study, they were also, it's a positive relationship, so the two variables move in the same direction. So if somebody was depressed at the start of the study, they were also more likely to be to have a higher secondary trauma score at 12 months. So if they're already depressed at the start of the study, it makes sense that throughout the course of the study, their secondary trauma symptoms would be a little bit higher perhaps than other folks who weren't already struggling with their mental health throughout the study, throughout the time frame of the study. So this 0.55 is interesting to me. It's not a very strong relationship, so it's still a pretty weak relationship, but it is a positive relationship. Also, we can see that the spouse or partner's perception of their spouse or partner's PTSD symptoms also had a relationship with how their secondary trauma was showing up. So if the spouse or partner perceived like, oh yes, my police officer spouse/partner has PTSD symptoms, so if I'm the spouse or partner of the police officer and I see that my spouse or partner has PTSD symptoms, I'm also more likely to have secondary trauma symptoms myself. So 0.64 here, it's showing the relationship between the spouse or partner's perception of the officer's symptoms, PTSD symptoms, connected to the secondary trauma symptoms that spouse or partner themselves is experiencing. So here we have another positive relationship. All right, this is kind of a little bit more complicated correlation matrix to understand just because the variables are a little complicated. We're going to come back and look at the same article example when we talk about linear regression as well. But know that when I present you with a correlation matrix, I'll intentionally choose one that's a bit more clear than this one, so you know what the variables that you're looking at are. When we move into talking about charts and how to interpret these types of things, this is another situation where a lot of patience is needed. You're not going to understand everything on the chart. For example, we're not even talking about these little stars and what this stuff means. We won't talk about that for a few weeks more now. So for now, go at the pace that matches you. When you're presented with information like this, break it down into little pieces, ignore the stuff that doesn't make sense to you right now, and try to focus in on the pieces that do make sense to you or that you are equipped to interpret right now. All right, that's it for this video, and we'll be back to talk about linear regression whenever you decide to watch that video.